Let us now look at the different algebraic structures of the natural numbers, the integer, rational, real numbers, and complex numbers. So let's start with the natural numbers, n. So in this case, something that we always, by this time we take for granted is that the sum of natural numbers is a natural number itself. Okay. For example, if I add together 101 plus 2, I get 103. No big deal. The product also works very well. Product of natural numbers is a natural number. Okay, in this case, I can also multiply the two numbers. 101 times 2 is 202. No problem. Here, I say no problem because both 103 and 202 are natural numbers. They belong to the set of natural numbers. But this is not true for the subtraction and the division. Okay, the subtraction and division. Okay, for example, let's say 101. If I subtract 2, there will be no problem. I will get 99. That's still a natural number. But let's say I subtract 103. In this case, what do I get? Well, if you're thinking -2, that's not a natural number. So it's not a natural number. Okay, so we fall outside of the set of natural numbers, so we cannot actually do the difference in every case. And the same is true for 101 divided by 2. Okay, this is also not a natural number. You may be thinking, yeah, okay, but that's a rational number, but that is a different set. Okay, here your only choices are the natural numbers, whole numbers. Okay, so what happened here? The sum is okay, the product is okay, subtraction and division not okay. Okay. So let's look at the what happens with the integer numbers. For the integer numbers, these ones already include the natural numbers, so everything that went well for the natural numbers is still going well, but they also include their additive inverses and 0. Okay, these are important. The additive inverses and the 0, we will get more in detail with these things later on. But for now, what is important here is that both the sum and the difference work okay. I mean the sum of the and difference of integer numbers are an integer number. Okay, so for example, now if I do 101 minus 103, I get -2, which is a number in Z, so no problem. Happy face. Okay. But the product is still okay. The division, not so much. So the product of integers is an integer. The division of integers, not always an integer. Okay, here the answer sometimes is not acceptable. So here we have the sum is good, the difference is good, the product is good, the division is not good. Okay. So you see we have fixed one of the two problems of the naturals, but we still have the other problem. So for that, we can move on to the rational numbers. Okay. These ones contain all integers and their ratios. Okay. In this case, the sum, the difference, the product, and the division the division as long as we don't divide by 0, okay, but of rational numbers give a rational number. Sometimes we say that the four operations are closed on the rationals, okay? The problem that we were having before, for example, 101 divided by 3, this was not in Z, in the integers, but it is a rational number, so it belongs to the rationals. So here, if you notice, the rational numbers have a richer structure than the natural numbers and the integers, okay? The structure of Q of the rationals is the structure of a field. And we will define this very carefully very soon, okay? For now, I just want you to know that there are other examples of fields. In fact, the real numbers and the complex numbers are also fields, okay? There are more complicated examples, but we don't need to go there, okay? So here, the takeaway of this video is to understand that the structure of field is important for us because it's the structure that the real numbers and the complex numbers have.